Hello friend, today I'm going to design a long column. The problem statement is given design RCC rectangular column of the size 300 cross 500 mm and the floor to floor height is given 5.6 meter and the material is used, that is the M30 grade of the concrete, and the grade of the steel is used F415. Okay, the beam is connected to the columns. The dimension of the beam is given to 30 cross 400 mm. Okay, and the effective cover of the column is given 50 mm. Okay, and the consider the effective length factor is given k is equal to 1.2 meter. Oh, sorry, 1.2 only. Okay, so this is the dimension of the column, that is the width is given 300 and the height is given 500. Okay, 500 mm, and the length of the column is given how much? 5.6. Okay, 5.6 meter. I hope it is clear. Now the axial load is given 1600 kilonewton and moment about the major and minor axis is given 45 and 40 kilonewton meter respectively. Okay, the floor to floor height of the column is given 5.6. Okay, so actually this three data is only came from the software. When you are using the software like the Stat Pro, you only provide the dimension of the columns, but after getting, you apply the various loaded like the beam of the beams, load from the beams, load from the slabs, and the load from the various like the live load, dead load. All these things are coming on the columns. So this load create the what? Moment about the major and the minor axis. Suppose this is the column here and the some beam is crossing. So this beam, or maybe there is some additional slab is there. So due to the effect of the beam and the slab, there is this some moment will will be generated on the what? Column. Okay, about the minor and the major axis. Okay, so that's why the moment will come. After getting the three factor, only the three things will come after software. After using the software like the PU and MUX and the MUY will come. After getting this, you have to design the columns. Okay, the length of the column is given 5.6 meter, and unsupported length you have to find out, because unsupported, because the beam is connected, so you have to subtract the height of the column. Okay, 5.6 minus zero point 0.4. This is the unsupported length of the columns. Okay, effective length factor is given k is equal to 1.2. So the effective length of the column about the both axes, you have to watch it about the both axes, LEX or LEY is equal to, you have to multiply with this factor. Effective length factor you have to multiply with the total length. Okay, that means 6.2. What is the effective length? Effective length, that means the length of the column is participate. Okay, the length of the column is participate during the load coverage. Okay, suppose I'm there are four cases generally in structure of mechanics. The next class I will take. So the four cases I will discuss about that. Suppose a column is taken and both end is fixed. So here the effective length will be the half. Okay, 0.5 L. One end is fixed, one end is free. So the effective length will be the two times of the length of the columns. Okay. So here the already the effective length factor is given 1.2 meter. 1.2. So you have to multiply to get the effective length of the column 6.2 meter. 6.24 is coming. So in next slide, Now stepwise step I will discuss very easy way. Okay, what you have to do first, you have to check whether this column is short column or long column. So to check, you have to go the clause 25 1.2 page 41 is 456. You have to check whether this column is comes under the short or the long columns. So what you have to do, you have to find out the slenderness ratio about the both axes, major axis and the minor axis both. So LEX by D is coming 12.48. That is the 12. That is greater than 12. That is okay. That is, it is the long column about the major axis. So about the long column about the y axis, you have to LEY upon B. You have, this is the B. Width is given 300. So you have to divide the total length of the effective length of the column divided by the width of the column. So you are getting the 20.8, that is greater than 12. That means this in both axes this is coming greater than 12. That means it defined that this column is what? Long column. Okay. I hope it is clear. So step one. Step one is to check. You have to classify the column, that is whether it is come under the short column or the long column. Okay. Now the step two. You have to. This column is long. So you have to find out the additional moment about the both axes. Okay, this due to the long column effect, you have to see the clause 39.7 page number 71 as per the IS 456. You have to find out the additional moment. That means the additional moment, actually the first moment you have got due to the various loaded act on the what? Act on the column due to the beam, slab and the live load, dead load. But here you have to find the additional moment because this column is long. So this is the MAX. You have to find the additional moment about the x axis, about the y axis. So MAX is equal to Q by D divided by 2000 L effective divided by the depth of the column is a whole square. That's why you are getting the MX is equal to 62.300 62.3 kilonewton meter. And for again you have to find about the y axis. You are getting the 103. Simply you have to divide the PU is what here? PU is the axial load. Factor axial load acting on the columns. Okay, B is what? B is here the width of the columns. Okay, that is 300. And about the 200, and it is a 62 point, that is the effective length of the column, and 300, that is the width of the column. You have to, you just got the MAY, that is the additional moment. Where it is in the code? It is given in the code page number 71. So this formula is given. Okay. Okay. So slenderness, cylinder compression of the member, the additional moment MUA, MUY shall be calculated by the following formula. This formula is given. So you have to find out the additional moment using this formula. Okay, here what is PU? PU is the axial load of the member. ADX is the effective length in respect of the major axis. LEY is the effective length respect to the minor axis. In both cases, we just got 60. Just we multiply the length of the column with what? Factor 1.2. And B is what? B is the depth here, and B is the width of the member. Okay. So now again we are coming on this slide. So we just got the additional moment. Now after getting the additional moment, you have to again you have to apply the moment reduction factor. Okay, this is a very important point you have to learn here. the moment reduction factor, that is the K. K you have to multiply with what? This is the you have to apply. You have to multiply with this K to the whatever the moment you have got in additional moment. Okay, so K is here. K is given. K you have to find using the formula PUZ minus PU upon PUZ minus PB. What is that? PU is the factor axial load, that is the 1600 that already given in the question, and PUZ is the ultimate axial load capacity of the column. This formula is given in the code also. Okay, and PUB, that is the axial load corresponding to the balanced failure condition. One by one we learned that how this two formula is used to get get its value. Okay, so here PUZ and the PV is given. Okay, PUZ and PV you have to find out using the code SP-16. Okay, so I'm going to the code and we see that how this formula is used in SP-16. Uh, page 171. Page 171. So the column is what? Our column is rectangular. Okay. So PUB here, PUB by FCK VD is equal to K1 plus K2 P by FCK. Okay. This is for what? Rectangle. When you are using the circular member, you have to use this formula. Okay. So how will you get the K and K2? Okay. The target is K1 and K2. PB, because I'm using this formula. Okay. So what you have to do for value of the K, first you have to find the D by D ratio. We already, because the effective cover is given 0.5, sorry 50 is given. So you have to divide with the total depth of the column, that is the 500, that you are getting the 0.1. So 0.1, that K1 value is you are getting what? 0.207. Okay. And so here from here you will get the PBX. Okay. PBX, you are getting the PB. So PB, simply you will multiply with all the data PB upon FCK. Simply from here you will get the PBX, and similarly you will get the PBY. Okay. See. So K's value you have to PUZ. PUZ is what is the formula PUZ? It is also given in the code. So what you have to do, formula use is already we have seen in the code SP-16, table number 16, table number 16. So here this is what? PBX and PBY. So for PBX you just find out the K value and K2 value using the code, and after getting that FCK already given, width of the column dimension is given. So the percentage of the steel, why I'm using the percentage of the steel? Because PT is here, PT by FCK. PT is here the percentage of the steel. Okay. So PT is given 3%. I'm using the 3% of the reinforcement uh, with respect to the concrete that is used in the column. Okay. So the steel percentage is 3%. I'm taking effective cover, that is D dash is equal to 50 mm. So D dash by D ratio is you are getting 0.1. So we have already seen in the table 16. So K1 and K2 value already you have to see using the chart. K1 is 0.27 and K2 is 0.082. Okay. So PBX So for pbx, what again you have to divide again for pbx, because here d dash by d ratio is 0.1. Now you have to again you have to find out the d dash by d ratio, p ratio. So whatever the value you are getting, you have to just uh, with respect to, you have to find out the value corresponding to that. So the now just you substitute pbx, we just substitute the value k1 and k2 value here, and the 3 is what percentage of the steel, and fck is here, the 30% 30 grade of the steel is given. So here you just got the pbx. Okay, what pb now you have to multiply with this factor, with the you just pbx you are getting, sorry, this value is okay 0.21. So pbx you just multiply with fck bd. So pbx you are getting 968.6 kilonewton. Okay, again for the y axis, whatever the calculation we have done for the x axis, okay, reduction factor from the reduction bending moment about the x axis, d dash by d ratio we have already discussed. Now about the y axis, what you have to do, again you have to find the d dash by d ratio, 50 by 300.16 corresponding to SP-16 table number 60. You have to again you have to find out the k1 and k2. Okay, again here you have to interpolation, you have to do the interpolation to get the k1 and k2. Okay, now pby you are getting using the formula, and the pby you are getting, finally you are getting the 874.35. Okay, reduction factor about the x axis, kx, just you have to put the value. Okay, pu z you have to use the formula, and the pu is also 1600, and puz, and about the pbx whatever the value you have got 968.6 about the x-axis, reduction factor about the x-axis you have to put here, and kx value is here, you are getting 0.7365. Okay, reduction factor about the y-axis, again same things, but only the change here, that is the pby. Okay, pby you have to put, you are getting ky. Okay, now the reduced additional moment, what you have to do, mx kx you have to multiply with kx factor about the whatever the additional moment you just got, so you have to multiply to get the reduced additional moment. This is the 45.884 kilonewton meter. Okay, about the y-axis, similarly about the y-axis you have to multiply with the ky factor with the additional moment about the y-axis, simply you are getting the may. I hope it is clear. Okay, what we have done here, simply I'm telling, after getting the additional moment here, whatever the moment we just got using this formula, because additional moment, why I'm using the why I'm finding the additional moment, because this column is long. After getting the additional moment about the x and y axis, you have to multiply with the work factor, that is the moment reduction factor you have to multiply with. And how will you get, using this formula? Okay, and the this formula you use, how will you get the pbx and pby? Simply suppose about the x-axis I am using I am finding the pbx. So you have to first you have to find the d by d ratio, and the using the after getting the d dash by d ratio, I will just go to the chart 16, table 16 in SP-16. So from there we will get the k1 and k2 similar, and again I will put the value in this formula, I will get the pbx. Similarly about the y-axis, again the same procedure, only the thing that will change, that is the b only. Okay, 0.167, and again I will go to the table number 16 and I will see that K1 and K2 value corresponding to the d dash by d v, and I will get, and I will put the value in this formula. I will simply substitute the K1 and K2 and I will get the PBY. After getting the PBX and PBY, I will just use the, I will find out the reduction factor about the x-axis, PUZ, that is the ultimate axial load capacity of the column. This formula, how will you use this formula is given in the code. Okay, page number 71, you will see there, and simply you will find out the PUZ, and after putting the all the required value, because already you have find out all the value, you will find out the kx value, that is the moment reduction about the x-axis. And similarly, same procedure you have to find out, the same procedure you have to apply in the for getting the reduction factor about the y-axis, and simply you will multiply with the additional moment, you will get the reduced additional moment about the x-axis, about the y-axis. I hope it is clear. Now, finalizing the initial moment, step 3. Step 1, we have checked the whether this column is long or the short. Step 2, we have just applied the additional moment, and after getting the additional moment, we just apply the reduced factor to get the reduced moment. And step 3, that is the finalizing the initial moment. Okay, clause 55.4, page number 42, IS 456. The moment due to the minimum eccentricity, you have to find what is the moment due to the minimum eccentricity. Suppose this column is given, and this is the major axis x, and this is the y. So suppose this is the ex, and suppose this point is, that is the ey. So we assume that the load is acting here. Okay, so we have to find the minimum eccentricity, or it should be greater than the 20. So it is greater than the 20, that means this is okay, it is safe. Okay, so we will find the moment minimum eccentricity about the x-axis ex. Simply L effective by 500 by d by 30, we are getting the 27.6. It should be greater than 20, that means this is okay. Okay, similarly we will find out the moment minimum eccentricity about the y-axis, that is the ey, le by 500 divided by b by 30, that we are getting 20.4 mm, that is greater than the 20, that means it is good, it is safe. Okay, then I'm getting the moment. Okay, mu x, this is due to what? Minimum, this moment due to the eccentricity. Okay, moment due to the minimum eccentricity, mux, that is the pu ex, is equal to, you have to multiply with the ex. Pu is what? Pu is here the factor axial load acting on the column, that is the 1600. You have to multiply with ex, that is the 27.06. You just got the mu x is 43.296 kilonewton. Similarly, mu y you have to find out using the same procedure. You simply multiply with the ey, you are getting the 32.64 kilonewton meter. Now here the moment what I'm getting 43.29 and 32.640. So the basic moment we have from analysis, MUX 45 kilonewton, it is greater. That means ki whatever the value you are getting due to the whatever the moment you are getting due to the minimum eccentricity, it is less than the basic moment, then it is okay. Otherwise, if this value is greater than the, that is the given moment, this moment is what? This moment is given in the question. See here, MUX, MUY. So this moment is greater than the minimum eccentricity. So again, the design will be based on this moment. Okay. Okay. The basic moment is here 45 or 40 kilometer. And the primary moment considered. This is the primary moment you have to consider because this moment is greater than what? The minimum eccentricity. The moment due to the minimum eccentricity. So you have to consider the moment that is given in the question. Okay. So the final moment, what you have to do, you have to add MUX or MAX. MX was that is the reduced moment. Okay, 45. This come here. This and the 45.88 that is the reduced moment. Okay, MAX. Clear? Similarly, you will get the MUY. Final moment MUY. So overall, the moment that is coming about the y-axis, that is the MUY is 113.607. So you have to design the column for this moment. Okay. I hope it is clear. Now check for the adequacy. Now what we have to do, MUX, MUX1, AN to the power n plus MUY or MU1 to the power n is less than 1. Now what you have to do, here what is the MUX? MUX here you are getting the 90, MUY 113.67. So for getting the AN value, clause number 39.6 page 71 IS 456 2000, you have to first you have to find out the PU upon PUZ. Okay, and after getting the PU ratio of the PU and ratio of the factor axial load acting on the column divided by the ultimate axial load capacity of the column, you are getting 0.475. So you have to find out the AN value corresponding to this formula. And how will you find that? So for I'm going to the chart, I'm going to the table number 71. So we just got the value of the ratio PU upon PUZ. Okay, PUZ is what? PUZ is you have to find using this formula. Okay, you have to find using the formula 0.45 FCK AC, area of the concrete here 0.75. Fy is the grade of the grade of the steel, AC is the area of the steel. We have already used the AC is 3%. Okay, so simply using this formula you will find out the PUZ. Okay, and MUX and MUY, how will you get? In SP-16 chart number 32, I will go and I will find out the MUX and MUY corresponding to the corresponding to the value. In this slide I will corresponding to that value. Okay, so I will check how will I first I will see that whether this formula is given and how will you find out the AN value. Okay, so I will go to the page number 71 IS 456. See here. See, the moment subjected to the combined axial load and the biaxial moment. It is the biaxial because the moment is given about the x and y axis in both directions. So it is the biaxial moment, biaxial bending. So you have to design the column axial load, because axial load is acting and the moment is also given in both x and y axis. That is called, that is the biaxial bending. Okay. So here we have to check whether this value is came less than 1 or not. So MUX, MUY, that is the moment about the x and y axis due to the design rule, because we just got the MUX and MUY, and MUX and MUY, that is the maximum uniaxial moment capacity for the axial load PU bending moment about the x and y axis respectively. Okay. X is related to the what? PU by PZ. We have already discussed PUZ. You have to use this formula. Okay. So PUZ or by PUZ is equal to 0.2 to 0.8. The value of the alpha is very linearly. Okay. That means if suppose if I am drawing the axis PU by PUZ alpha. So if PU by PUZ is 0.2, so the value of the alpha is 1, and PUZ by 0.8, so this value is what? 0.2, sorry. So this vary linearly. So whatever the value you are getting for PU by PUZ, so you will get the value of the alpha using the linear interpolation method. Okay. Using the linear interpolation method, you have to find out the value of the A. Okay. Corresponding to the value of PU by PUZ. Okay. So here PU by PUZ is what? I am getting 0.47, 0.475. So we just use the interpolation method. Okay. Interpolation method, and we just got the value of the alpha AN, that is the 1.49. Okay. And how will you find the MUX and MUY? Okay. MUX and MUY you have to find out. See, a step used to obtain the MUX and MUY. So you have to calculate the non-dimensional axial load. Okay. First you have to find the PU by FCK BD. Okay. You have to find 0.35 PU by FCK BD. That is the PU is 1.6 in 10 to the power 6 kilonewton, because it is given in kilonewton. We have just converted in Newton, so you have to multiply with 10 to the power 3. FCK is given, and B is given 300 mm, and D is given 500 mm. Okay. So PU by FCK BD is, we just got the point 0.356. Okay. So, and one value we have got, and again we have to find out the PT by FCK ratio. That is the PT by FCK ratio. Why I am finding that? Because the chart in SP-16 chart 32. Okay. See, chart 32. So corresponding to the D by D ratio, D dash by D ratio, that be 0.01. So first you have to think why I am using this chart. Because first condition is that three condition I have. I have the D dash by D ratio is 0.1. Okay. That is okay. What the grade of the steel I am using the 415. Okay. Steel that I am using in the column, that is distributed in only both sides. This is not in all sides. Okay. What is the meaning of all sides? Suppose column is I'm taking, and the steel is I'm providing like this. So this reinforcement is distributed in what? All side, four side. So here the reinforcement is distributed equally on the equal side. Okay. That's why I'm using this chart. So what you have to do, PU by FCK BD, what I'm getting, the value we have already find out the value, that is the what? PU by FCK BD, that we just got the 0.356 to corresponding to that value you have to go point 3 point how much, 0.356. So 0.356, that value will come, and this chart is what, this is the PT by FCK. Okay, so PT by FCK, sorry, PT by FCK is 3 by 30. Okay, 3 by 30, that is the point 1. 3 by 30, that point 1. So you have to see here point 1, and the corresponding to the value you have to find out. Suppose 3 point something a point 1, and you have to find out the value, that is the, you will get whatever the value you are getting, that this will give the mu upon FCK BD square. Okay, that will give the ultimate moment. Okay. Okay, so see, we have seen corresponding to the PU by FCK BD and D dash by D, zero point 0.1 percentage of steel is given 3%. So using the SP-60, so from the 30 chart number 32, we just got the MUX. Okay, so MUX, simply you will multiply the FCK BD square, you will get the MUX. So I hope it is clear how will I get the MUX1. Similarly, the bending moment about the minor axis you will get using the same chart. Only the difference you have to multiply with what? That is the d square, small d, b square, sorry, b square. You have to multiply with the b square. You will get the 162 kilonewton. Okay, I hope it is clear. So you just got the bending moment about the major axis, bending moment about the minor axis. I hope it is clear. So again, I'm moving on the slides, step 4. So what you have to do, MUX you just got, MUX1 you are just, you already got the value, alpha value you just got, and similarly MUY and MUY1 you just got. So you have to put the value. Simply you see here. You have to check this value is coming less than 1 or not. So after putting the value, after solving this equation, I am getting 0.759. That is less than 1. That means the design is safe. Suppose if it is coming greater than 1, so what you have to do? So what is in your hand? What should I change? Tell me. What you have to do? You have to increase the percentage of the steel. You have to change the dimension of the column. Only the things you will change. You will change the grade of the concrete. You have to change the grade of the steel also. So there are, that's why the design is complicated. Okay, so design is difficult. So uh you have to check again and again, trial method. You have to use the trial again and again until this value is coming less than 1 or not. Okay, so I'm moving on the slide. Same AC. Now that means we just got the value is less than 1. Okay, so that means the percentage of the steel that we have assumed 3%, that is okay. That means it is okay. It is good. It is safe for our design of the column. Okay, whatever we have considered the steel, because the steel it is in our hand now. You can change the steel grade, concrete grade, grade of the concrete, grade of the steel, dimension of the steel, dimension of the column. Okay. So now whatever the value we have considered, the dimension, the grade of the steel, the grade of the concrete, and the percentage of the steel, whatever you have assumed, that is the 3%. That means our assumption is good. Our assumption is uh, give our safe design. Okay. So now that means it is safe. So what you have to do? Again, you have to find out the reinforcement. So it now it's easy. Percentage of steel you have assumed the 3%. Gross area that is you have that is 500 cross 300, that is the 15,015,000 mm square. So area of the steel you will find out the 4500 mm square. Okay. So you provide the 28 bar. You can change. Now it's up to you. Okay. Yours column is safe. It's up to you how much, what is the diameter of the steel that you are using, 20 25 30 Now it's up to you. So I am here, I am just assuming here 28 bar. Okay. So area of the one bar is 5 by 4 d square. D is here 28. Okay. So you just got the area of the steel is 1 bar, 615.75 mm. So number of the bar, you simply divide the total number of the total amount, total area of the steel with the one area of the one steel. So here you are getting the 7.3. So if we just equivalent the 8 number of the steel. Okay. So provide the, now you have to provide the 8 bar of 28 of the dia. Okay. Okay. That I'm talking about the longitudinal bar. Okay. What is the longitudinal bar? Suppose this column is, this is a side. That means we are providing the 8 number of the longitudinal bar. Okay. The dia of this bar is 28 mm. And how will look that? How will look like? This will look like that. Okay. Now, design lateral, design of the lateral tie. What is lateral tie here? Suppose this is the column. So you have observed in the side, this is what the lateral tie. Okay. Why it is provided in the column? And what is the spacing of this lateral bar? Okay. Actually in beam, it is called stirrup. Suppose this is the beam. So you have seen that this is the, this tie bar is used, but there in case of the beam it is called the stirrup. Okay. Stirrup. So IS code has already specified the stirrup dimension, stirrup, and what is the spacing in case of the beam, but I am discussing here about the column. Okay. So first we'll find out the what is the diameter I have to use stirrup. So IS code is telling that you have to use the dia is 1/4 of the longitudinal bar. Okay. That means 28 by 4. That is 7. That you have to equivalent because 7 dia bar is not available in the market. So you have to use the 8 of the dia. Okay. Now, dia you just got. Okay. So what is the spacing? So you have to find the least of these three cases. Least lateral dimension that is the 3 and the 16 time of the what? 16 time of the longitudinal dia, longitudinal bar dia. Okay, that is the 21 is 4 and the 3 mm. Whatever the value you are using, whatever the value you are getting, you have to take the minimum value among these three one. Okay. So, but I am providing here the 250. Okay, for the safe. Okay, you will provide 3 mm minimum because you are just going according to the core. That means ki your design is safe. But I am minimize the spacing of this tie bar for our good. Now, the main question is that why I am using the lateral bar? Why it is? What is the purpose for using the lateral tie? Because whenever you are apply the load, if the load is heavy, so it's resist to bulge. Okay, resist to bulge, and it's try to hold the longitudinal bar. That is the purpose of using the lateral tie. Okay, in case of the column. Okay, but this is but in case of the beam, its work, the purpose of using the stuff is totally different that is used in the column. Okay, so the final schedule, the section dimension is 300 cross 500 mm. Main dia is 8 in number, of dia 28 mm. Lateral tie you are using the T, that is the dia is 8 mm, spacing is 250 mm. Okay, your design is okay. Thank you so much. If you are getting the any doubt in the slides, so you have to ask the question and write your question in the comment. I will reply as soon as possible. Okay, thank you so much.